You ever look at a solar panel and wonder how it actually works? How does it just sit there and turn sunlight into electricity? Well, the answer is this amazing and frankly pretty weird phenomenon called the photoelectric effect. And it's a story that didn't just give us new tech, it completely blew up our understanding of what light, and even reality itself, actually is.
Okay, so let's get right into it. At its heart, the idea sounds super simple. You take a piece of metal, you shine some light on it, and boom, little particles called electrons start popping off the surface. The main characters here are just light, metal, and those electrons making a break for it. Sounds pretty straightforward, right? Well, as physicists found out, it was anything but.
Because right away, scientists slammed into this bizarre mystery. Imagine you're shining a dim red light on some metal, and absolutely nothing happens. What's the logical next step? You'd crank up the brightness, right? Get a super powerful, blindingly bright red light. But when they tried that, still nothing. No electrons. This one observation just didn't make any sense, and it set the stage for a complete revolution in physics.
To really get why this was such a mind-bender, we need to look at the strange new rules that came out of these experiments. This wasn't just some quirky little effect. It was a phenomenon with its own peculiar laws of nature.
First up, let's get our terms right. The electrons that get knocked loose by the light, they get a special name: photoelectrons. The photo part comes from the Greek word for light, so it's a super literal name. These are literally light electrons. And here is the first and maybe most important rule they figured out. It turns out not just any light works. For every metal, there's a specific minimum frequency, a specific color of light, you could say, that you need to even get started. We call this the threshold frequency. If your light's frequency is below that line, I don't care how bright you make it. You could shine a light as bright as the sun, and you would get absolutely nothing. Not a single electron.
So you can see how this was becoming a massive headache for the physics of the time. All the established theories, the very foundation for how they understood energy and light, just couldn't make heads or tails of it.
This slide really puts the problem in sharp focus. See, back then, everybody agreed light was a wave. So wave theory predicted that a brighter, more intense wave should have more energy and it should knock electrons out with more speed. But what did the experiments show? Brighter light just knocked out more electrons, but they all had the same energy. The old theory also said any frequency, any color of light should work if you just shine it long enough for the energy to build up. But in reality, nope. Below that threshold frequency, you could wait until the end of time, and nothing would happen. And finally, the old theory said there should be a little time lag, right, for the electron to absorb enough energy to escape, but what they actually saw, the electrons were ejected instantly.
So the bottom line is, this wasn't just a tiny mistake in the calculations. The predictions were 100% wrong. The rulebook that physics had been playing by for centuries was officially broken.
And this is where a young, unknown patent clerk named Albert Einstein steps onto the stage. In 1905, he came up with an idea so bold, so revolutionary, it solved the entire mystery in one brilliant move.
Einstein's idea was just wild. He basically said, what if we've been thinking about light all wrong? What if it's not a smooth, continuous wave, but instead it comes in little, individual packets of energy? He called these little energy bundles photons.
And here is the truly genius part. Einstein said the energy of one of these photon packets has nothing to do with how bright the light is. It depends only on its frequency, which is what our eyes see as color. So high-frequency light, like blue or UV light, is made of super high-energy photons. And low-frequency light, like red light, is made of weaker, lower-energy photons.
Okay, the best way to get your head around this is with an analogy. I want you to think of these photons as tiny little energy bullets being fired at the metal. An electron only gets knocked out if it gets hit by one single bullet that has enough power to do the job.
This bullet analogy just makes everything click, doesn't it? The light's intensity, its brightness, that's just the number of bullets you're firing per second. But the light's frequency, its color, that's the power of each individual bullet. And that's what explains the whole mystery. Firing a billion weak, low-power bullets of red light will never do what one single high-power bullet of UV light can do.
So every metal holds onto its electrons with a certain amount of energy. You can think of it like an escape fee or a cover charge at a club. We call this the work function. For an electron to get out, it has to be hit by a single photon bullet that has more energy than that fee. If the photon's energy is too low, it's a dud. It just bounces off. It can't pay the price of admission.
Now, a beautiful theory is great, but science is all about proof. And the proof for Einstein's idea was so elegant, so simple, it was hidden in a straight line on a graph.
Einstein's whole theory can be boiled down into this one perfect little equation. It basically says the leftover energy of the electron, its kinetic energy, how fast it's moving, is equal to the energy of the photon that hit it minus that escape fee, the work function.
And here's the magic. If you remember anything from math class, you might recognize that equation. It's the exact same format as the equation for a straight line, y equals mx plus c. And that makes a very specific, testable prediction. If you plot the energy of the electrons you measure against the frequency of the light you're using, you should get a perfect straight line. And guess what? When they ran the experiment, that's exactly what they found.
And this graph is like a treasure map to the secrets of the universe. The steepness of the line, its slope, actually gives you Planck's constant, a fundamental number that's literally woven into the fabric of reality. Where the line crosses the horizontal axis, that's the exact threshold frequency for that metal. And where it crosses the vertical axis, that tells you the work function. It's all right there in one simple line.
So what does this all mean? That graph was the smoking gun. It was the undeniable, rock-solid proof that Einstein was right. Light isn't just a wave, it also acts like a particle. This was the moment the quantum revolution truly began.
And this wasn't just some abstract idea for physicists to argue about. This discovery has had a huge impact on the world we all live in, powering technology you probably use every single day.
In fact, the discovery was so important that in 1921, Albert Einstein got the call from Stockholm. He was awarded the Nobel Prize in Physics. And get this, it wasn't for his more famous theory of relativity, it was specifically for figuring out the photoelectric effect.
And its legacy is all around you. Those solar panels on your neighbor's roof, they are literally using this exact effect to turn photon bullets from the sun into a flow of electrons. You know, electricity. The sensor inside your digital camera or your phone, it's basically a tiny grid of photoelectric devices. Even the automatic door at the grocery store that opens when you walk up to it, that's often the photoelectric effect at work.
So we end up right back where we started, with this wonderfully weird truth. The photoelectric effect proved that light, something everyone knew was a wave, can also act like a particle. This idea, this wave-particle duality, is a cornerstone of quantum mechanics, and it leaves us with one heck of a question. If light can lead a secret double life, what else in our universe has a dual identity we haven't discovered yet?